Hi, I'm Dr. Frank Summers of the Space Telescope Science Institute. Welcome to Hubble's Universe Unfiltered. Today, we're going to talk about the next big thing in space astronomy. But we're going to start with the current big thing in space astronomy, which is, of course, the Hubble Space Telescope. This is the launch of the Hubble Space Telescope back in 1990, placing Hubble in orbit above Earth's atmosphere. And that's the important thing, that it's above Earth's atmosphere, which gives it an incredible view of the universe. Now, Hubble has been up there for over 20 years, and it has seen an amazing number of things. We've seen giant dust storms, planet-wide dust storms on Mars. We've seen not one, not two, but 3 red spots on Jupiter, these giant storms on Jupiter. We've seen giant star clusters containing tens of thousands of stars, and we look deep inside them to see the wide variety of stars that inhabit there. We have seen the stars as they're being born in these small clusters and in these giant vast nebulae where thousands of stars are being formed. We have seen stellar death, some that go gently blow off their outer layers, and some that explode as these vast supernova explosions. We have seen spiral galaxies, we've seen elliptical galaxies, we've seen combination galaxies called lenticulars that are half spiral and elliptical. We have seen galaxies in pairs that sometimes are interacting and stripping each other apart. We see them in groups, we see them in vast clusters of thousands of galaxies. And we've even looked all the way across space with the Hubble Ultra Deep Field. This image is the deepest visible light image ever taken of the universe. And in a very small region of the sky, Hubble finds over 10,000 galaxies. It looks as far out into the universe as we can see. By measuring the distances to these galaxies, we can give you a scientific visualization of what it would be like to fly through this image. The camera is just going to take a straight line path through the Hubble Ultra Deep Field. The galaxies are placed at their distances relative to one another out in 3D space. As we fly through, you can see that the galaxies have a wide variety of shapes and sizes. You've got small galaxies, you've got big galaxies. And what's really cool about this image is that as we go further out into space, we're also looking farther back in time, because the light from these distant galaxies has taken billions of years to reach us. We see them not as they are today, but as they were billions of years ago. Looking out into space is also looking back into time. You'll notice that the visualization ends with a black screen. Does that mean we've reached the limits of space? We've seen all the galaxies there is to see? No. Instead, we've reached the limit of what Hubble can see, because Hubble observes invisible light, and the universe is expanding. Light that travels across the expanding universe, its wavelength gets stretched along with the expansion of the universe. The light from very distant galaxies has its light stretched, and it goes from short wavelength to long wavelength. In visible light, the longer wavelengths are red, so we call this redshift. So the galaxies that are most distant appear redder. Here are some nearby galaxies that appear mostly white, some medium distant galaxies whose wavelengths have been stretched and now they appear more yellow, and these most distant galaxies that appear very red because their light has been stretched toward the red end of the spectrum. Well, what about the galaxies beyond this? Their light has been stretched so far, they're not observable in visible light. Instead, we need to observe in infrared wavelengths. The light has been stretched to the infrared. Now you might say, well, why haven't we done this before? Well, of course we have. Hubble is NASA's great observatory that observes in visible light, and the Spitzer Space Telescope is NASA's great observatory that observes in infrared light. And Spitzer has done a fantastic job of observing in infrared. Hubble's main advantage is that it has incredible resolution. Getting up above Earth's atmosphere gives it the best resolution in visible light. And so this is one of its most famous images, the Whirlpool Galaxy, and you can see it's got incredible detail. If I showed you a ground-based image of the Whirlpool Galaxy, well, it doesn't have anywhere near the same detail. This is Hubble, and this is ground-based. So you can see what Hubble's main advantage is. But if we take this image and compare it to Spitzer's image, well, you can see the bright regions here we see invisible light, and here's what Spitzer sees. The bright regions that Spitzer sees are actually dark in the visible. So here's the visible, infrared. Visible and infrared. Spitzer gives us a whole new view. It gives us a different way of viewing objects in the universe. However, its resolution is pretty faint compared to Hubble. Hubble has much, much better resolution. So in order to see these most distant galaxies, what we want is a telescope that has the resolution of Hubble and the infrared wavelengths of Spitzer. That one hasn't been launched yet, but it will be, and it is the James Webb Space Telescope that will launch in 2018. The James Webb Space Telescope has a much larger mirror than both Hubble or Spitzer. And the James Webb Space Telescope has a wavelength coverage that's in between. Hubble covers the visible light and a little bit into the infrared. Spitzer covers a lot of the infrared, and JWST covers just a little bit of the visible and on into the infrared. This is the observing region that astronomers have determined will provide us the most science for the next generation space telescope. Now, it's a really big deal, and you can tell because this is a life-size model of the James Webb Space Telescope down at Goddard Space Flight Center. Now, the first thing I thought upon seeing something like this was, how the heck are they going to get that into space? Well, they've got an amazing video because this is not just an infrared telescope, it's also the origami telescope. This telescope will start up, folded up like this in the top of a rocket, and on its path to its observing site, it will actually unfold. The Webb telescope will begin its unfolding by opening its forward and aft shrouds. The telescope assembly will rise up, and then as it becomes a rather slow process of unfolding its giant sun shields. These sun shields are about the size of a tennis court when unfurled, and they take quite a while to unfurl. Once they're stretched out, there are 5 layers of this sun shield, and if you look carefully, you can see each corner of the sun shield being slowly separated so the 5 layers are apart. After the sun shield has been unfurled, then we get the main mirror assembly, bringing the secondary mirror down into place, and snapping the wings of the mirrors around to complete the mirror face. The James Webb Space Telescope will have the sensitivity necessary with this giant mirror to observe in infrared wavelengths. It's not just the size of the James Webb Space Telescope that will enable it to do cutting-edge science, it's also its location. JWST will be located at what we call the L2 point, or the Lagrangian 2 point. And this is a gravitationally stable point that always stays outside of Earth. And for the James Webb Space Telescope, both Earth and the Sun will always be in the same direction. That's important because heat destroys infrared observations, and you want to keep your 2 major sources of heat always in the same direction. So this giant sun shield that we have here will always have the Sun and the Earth in the same direction, and the 5 layers of sun shield will passively cool the telescope. The difference between the hot side and the cooled side will be almost 600 degrees Fahrenheit. That will enable JWST to look deep into the universe and see what Hubble can't. So if we look into that Hubble Ultra Deep Field, there are some pullouts of it. You can see the big galaxies, and you can see the medium galaxies, and you can see these tiny small galaxies. Well, the most distant galaxies we've seen in the Hubble Ultra Deep Field are these tiny little red dots. Now, they're red because they've been redshifted. They're tiny, well, because they're far away, but also because they're early galaxies. As I said, looking out into space is looking back into time, and these are newborn galaxies. These are toddler galaxies. These are the young galaxies in the universe. If we want to see even further, we need to look with JWST in the infrared and look past what the Hubble Ultra Deep Field can see, look all the way through that to see the first galaxies in the universe. JWST will see the baby galaxies in the early parts of the universe. We'll be able to see the formation and development of galaxies across time. How cool is that? But that's not it. That's not all JWST does. JWST will also look at the formation of stars. This is one of Hubble's most famous images, the pillars in the Eagle Nebula. And there are stars being born here. But looking in visible light, you can't really see those stars. If instead we have an infrared view of those pillars, you can see the stars forming in the tops of those pillars. Looking at infrared light can look through the dark dust that appears in visible light and see what's happening inside. If we go to the Orion Nebula, one of the closest star-forming regions, we can look in there and see amazing things in visible light, but in infrared, you can see all the stars that are forming inside that nebula, not available to Hubble's vision. And what's further, in the Orion Nebula, we see these dark dust disks. We see these disks around stars where planets are being formed. We want to be able to look into those disks. We want to be able to see the planet formation within those disks using infrared light. Now, I got to say, this is a fanciful artist conception. This is not what JWST will see, but it gives you an idea that we want to be able to see the birthplaces of stars. What's more than that, we actually want to see the planets themselves. Here is an infrared view of a star called HR 8799. And this star has 3 planets orbiting around it. You can't see them, but if you subtract off the light of the star, you can see these 3 dots here. Using very careful subtraction, you can actually see the planets orbiting around it. And you need infrared light to do that because planets emit most of their light in the infrared. But let's take it one step further. We want to know about those planets. And some of those planets, from our point of view, will actually pass in front of their star. And the light of the star will go through the atmosphere of those planets. And if you take a picture of the star and then a picture of the star with the planet in front of it, you can subtract off and get the light from the atmosphere of that planet. We can start to characterize the atmospheres of other planets. And that's really important. Let me give you an example. Here are 3 objects, and these are their infrared spectrum. So this is the intensity of light across infrared wavelengths. And you can see what these 3 spectra have in common is that all of them have this dip here, which is the absorption by carbon dioxide in their atmospheres. But this middle planet here, it has absorption by ozone and absorption by water. This is the difference between the spectra of Mars, Venus, and Earth. The planet with life has a different spectrum. The first signature of life elsewhere in the universe will not be little green men in flying spaceships. It will be the detection of atmospheric signals that indicate biological activity on a planet around another star. This is amazing science, and the James Webb Space Telescope will make it possible. Now, when are we going to be able to get this? Well, I told you earlier, it's not going to launch until 2018. It's going to launch on an Ariane 5 rocket, and up in the top of the rocket, that's where the James Webb Space Telescope will be folded up. Yeah, that's a long way away, but so much has been done already. The mirrors, all 18 of James Webb Space mirrors have been fabricated and are flight ready. The instruments that are going to take these amazing observations, several of them have been delivered. They are in the final stages of getting ready. We have the sun shield, the giant sun shield in the process of being fabricated. We have to take all those elements together, combine them, and test them. And for that, we are going to use one of the largest vacuum chambers ever. You can see the people here. This is the giant vacuum chamber in which they tested things for the Apollo moon landings. The entire James Webb Space Telescope assembly will be put together into this and flight tested. That's what's going to take several years before we get to launch JWST and send it out to do its science. So in 2018, the James Webb Space Telescope will be out at the Lagrangian 2 point. It will be able to take incredible infrared images of the universe. And it will send back to us information about the development of the most distant galaxies, the earliest galaxies, how galaxies formed and developed across their lifetimes. We'll look at star formation, we'll look at planet formation. We'll be able to see those planets, and just maybe we might get evidence of life on other planets. All of that will be enabled by JWST. And that amazing science, that is the reason why it is the future of space astronomy. Thanks for listening today. We'll see you next time on Hubble's Universe Unfiltered.